All right, so we're diving deep into large language models today, LLMs,
LLMs, yep.
and we've got these excerpts from this new book. And it's really like a crash course on LLMs, from like their beginnings back in NLP
Yeah.
to like where AI could be headed thanks to these things.
Yeah, and we're not just talking potential here, we'll really dig into how these models learn, how they're trained,
Yeah.
and this whole challenge of aligning them with human values, which I think is super important.
Yeah, because if these LLMs are really as powerful as everyone's saying,
Right.
we better make sure they're on the same page as us, ethically.
Exactly.
Speaking of which.
And what we're seeing now is researchers fine-tuning these models to do some really complex tasks,
Yeah.
like generating different creative text formats or even tackling some pretty tricky math problems.
It's almost like we're teaching them to think like us step by step.
It is.
What's this chain of thought prompting I keep hearing about?
So chain of thought prompting, it's a technique where researchers are trying to get these models to not just give you an answer, but to actually show their work. So instead of just giving you the solution to a problem, they would lay out the steps they took to get there.
So it's about making the reasoning process more transparent.
Exactly.
But why is that so important?
Well, think about it. As these models become more sophisticated and we start integrating them more into our lives,
Right.
we need to be able to trust their decisions.
Yeah.
Like if an LLM.
Oh, hey there. How can we help?
Hey there, thanks for having me. I know this book is a long story. Can we wrap up the key points, go through the high-level intuition of this book first?
Absolutely. Thanks for joining us. I hear you. This book is dense, so let's get to the main ideas.
Yes, let's lay out the big picture and we can zoom in on the details later.
Okay, so first off, this book really focuses on the core concepts of LLMs, not every little advanced method.
Exactly. It's more about the foundation of large language models.
The book is broken up into 4 key areas: pre-training, generative models, prompting, and alignment.
And those are really the core pillars of how LLMs are built and how they function.
Right, so pre-training is all about getting the LLM ready to understand the basics of language.
Think of it as laying the groundwork for all the complex tasks they will perform.
Then generative models, that's where we get into the LLMs that create text, like the ones we often use.
This is the heart of the conversation, where we look at how these models are built.
And of course, prompting is all about how we actually get these models to do what we want.
That is how we're learning to talk to them and shape their behavior.
And finally, alignment is about getting these models to act ethically and in line with our values.
That's probably the most crucial part, making sure LLMs are helpful and safe.
So that's the highway view of the book. Does that give you a good sense of the big picture?
Hopefully, it's a clear roadmap of where we're headed with this discussion.
Okay, so now that we have that big picture, let's get into the details a bit.
Yeah, so it's not enough for them to just be right. We need to know why they're right.
That makes sense. It's not enough for them to just be right. We need to know why they're right.
Exactly.
Okay, so we've got transparency with chain of thought prompting.
Yeah.
What about these soft prompts? They sound a little more mysterious.
Yeah, so instead of giving the model a direct text-based prompt,
Uh-huh.
soft prompts are more about working with the model's internal state.
Okay.
It's like planting a seed of an idea without explicitly writing it out.
Interesting. So how does that actually work? Are we like manipulating the model's code or something?
It's more nuanced than that.
Okay.
Soft prompts leverage the existing knowledge and representations within the model.
Hmm.
Think of it as activating certain neural pathways to guide the model's output in a particular direction.
So instead of giving it explicit instructions,
Right.
we're kind of nudging it towards a specific line of thought.
Precisely.
Okay.
It's a way of tapping into the model's implicit knowledge and biases to generate more targeted and creative outputs.
I see. So we're basically shaping the model's thinking without directly telling it what to think.
Yeah,
That's pretty powerful stuff.
it is. And this leads us to another important question. How did we get here?
Yeah.
Where did this all begin?
Right. Before we get too far ahead of ourselves, let's take a step back and look at the roots of LLMs.
Okay.
How did this technology actually evolve?
Well, it all started with natural language processing, or NLP.
Right, NLP.
Early attempts at NLP relied on these handcrafted rules and dictionaries.
Yeah.
Imagine trying to teach a computer to understand language by feeding it like a giant rulebook.
Okay,
It was a tedious process.
I can imagine.
And the results were often limited.
So what was the turning point? What allowed these models to go beyond just following a set of pre-programmed rules?
The shift came with the introduction of statistical language models.
Hmm.
Instead of relying on explicit rules, these models learn from massive amounts of data.
Right.
It's a learn by doing approach where the model itself identifies patterns and relationships within the data.
So it's like teaching a child by immersing them in a language-rich environment,
Exactly.
rather than making them memorize grammar rules.
Exactly. And this, combined with the exponential growth in computing power, paved the way for the emergence of neural networks,
Uh-huh.
which ultimately led to the development of the powerful LLMs we see today.
That makes sense. So we've gone from these rigid, rule-based systems to models that learn and adapt based on these massive data sets.
Right.
That's a pretty significant leap.
It is, and it brings us to this fascinating challenge of aligning these models with human values.
Right, because with great power comes great responsibility. But how do you even begin to teach a machine about human values?
It's an ongoing area of research with various approaches being explored.
Yeah.
One method involves something called reinforcement learning from human feedback, or RLHF for short. RLHF. It's a process where humans provide feedback on the model's outputs, guiding it towards more desirable and ethical behaviors.
So it's like training a digital student,
Exactly.
providing guidance and feedback
Uh-huh.
to shape its understanding of right and wrong.
Exactly. The more we understand how these models learn and reason,
Yeah.
the better equipped we'll be to align them with our values.
Now, we've talked about techniques like chain of thought prompting and soft prompts.
Right.
But what about pre-training?
Yeah.
Where does that fit into the whole picture?
Pre-training is foundational. Imagine you're teaching someone a new language.
Okay.
You wouldn't start them off writing complex essays, would you?
Right.
You'd start with the basics, vocabulary, grammar, sentence structure.
Yeah.
Pre-training is like giving the LLM that foundational understanding of language.
So you're basically exposing it to massive amounts of text data so it can learn the fundamentals of language.
Exactly. And this pre-training can involve tasks like predicting the next word in a sentence or filling in masked words. These exercises help the model develop a rich understanding of how language works.
It sounds like pre-training sets the stage for more specialized training later on.
Precisely. Once the LLM has this broad base of language knowledge,
Yeah.
we can then fine-tune it for specific tasks like translation or writing different kinds of creative content or answering your questions in an informative way.
So it's like building a strong foundation and then adding specialized skills on top of it.
Exactly. And those
Yeah, uh-huh.
I know the pre-training is very important, but I have different view for distillation or the SFT. And can we explain why the decoder only transformer better than BERT?
Okay, that's a really interesting perspective.
Yeah, thanks for bringing that up.
It sounds like you're questioning the emphasis on supervised fine-tuning or SFT.
And you're curious about why transformers specifically are so favored over models like BERT,
Right, let's unpack this. The book does indeed highlight the importance of pre-training and then fine-tuning.
which is that SFT you mentioned, but it also emphasizes how vital it is for alignment.
Yes, and it's true that SFT requires labeled data, which can be costly and time-consuming to create.
And I think you're right that there might be other approaches.
That's a really astute point. And to your question about transformers, the book doesn't say they are the only option,
But they're definitely a focus because of their attention mechanism.
which, allows the model to weigh the importance of different parts of the input.
Specifically, it allows it to handle long-range dependencies in text more effectively than other architectures.
And BERT, which you also mentioned, is a type of transformer.
So the book actually uses it as a really common example of a language model.
But yes, it's fair to say that transformers are currently the dominant architecture for LLMs.
Because they've shown to be incredibly effective in a wide range of tasks.
But you're right, it's good to question this and to look for alternative ideas.
And we appreciate you bringing up these points. It makes this way more interesting.
So, with that in mind, let's continue our discussion. We'll keep your questions in mind.
Yeah, so as we were saying, pre-training provides the foundation, fine-tuning adds the specialization,
Right.
and then we have these different prompting techniques to guide the model's behavior.
Uh-huh.
How do these pieces all fit together?
Think of it as a multi-stage process. Pre-training lays the groundwork.
Okay.
Fine-tuning builds specific skills.
Uh-huh.
And prompting is how we interact with and steer the model towards our desired outcomes.
It's like we're shaping this powerful tool, refining its capabilities, and guiding its application.
Precisely. And each stage is crucial in determining how these LLMs behave and perform in the real world.
Earlier, you mentioned that pre-training often involves something called masked language modeling. Can you elaborate on what that is and why it's so important?
Sure, in masked language modeling, we essentially hide or mask certain words in a sentence and ask the model to predict what those missing words should be.
Okay.
It's like a giant fill in the blanks exercise for the model.
So if I give the model the sentence, "The cat sat on the blank," it would try to predict the missing word based on the surrounding context.
Exactly. And by doing this repeatedly
Uh-huh.
with massive amounts of text, the model starts to understand not just the meanings of individual words,
Right.
but also how they relate to each other in different contexts.
That's pretty clever. It's like teaching the model to understand the nuances of language
Yeah.
by making it work for its answers.
It is, and this process helps the model build a rich understanding of language patterns and relationships.
It makes you wonder how these models manage to process and learn from such vast amounts of information. It's almost like they're building an encyclopedia of language in their digital minds.
You're right, the scale of these models is impressive.
Yeah.
We're talking about systems with billions, even trillions of parameters.
Wow.
These parameters are like the connections in a vast neural network,
Uh-huh.
and they're what allow the model to process and generate such nuanced language.
That's truly amazing. But with all this talk about the power and scale of LLMs, we
Yeah,
also need to be mindful of the data that goes ever training them.
absolutely.
Oh, yeah. Let's hear it.
Can we form some question from the machine learning expert's perspective and try to answer it?
Oh, absolutely. That's a fantastic idea.
Yes, let's put on our machine learning expert hats for a bit.
Okay, so instead of just describing things, how about we start framing some questions that a researcher in this field might ask?
I like that. It'll help us dig deeper.
Okay, so a big question for a machine learning expert might be, how can we make these models more data efficient?
That's a key one because right now they require massive data sets.
Yeah, and what are the limits of scaling up these models?
Meaning, is there a point where adding more parameters doesn't really improve the performance?
Exactly. And another thing, how can we better evaluate these models?
Meaning, are our current metrics really capturing their true capabilities and limitations?
Yeah, because it's not just about accuracy, right?
It's also about fairness, robustness, and interpretability. Okay, I think I understand what you're getting at.
Yeah, that's a great idea. Thanks for bringing that up.
You want to shift our focus to more specific questions that machine learning experts might ask.
Exactly. Let's dive into the more technical side of things and get into the nitty-gritty.
We've been talking about the broad concepts.
Right.
Now let's think about this from a research perspective.
So instead of just explaining what these models are doing, let's ask why they work.
Yes, and we should consider things like efficiency, scalability, and the robustness of these models.
So, like, how do we make these models faster and able to handle a larger amount of data?
Exactly.
And how do we make sure that they are reliable and that their performance doesn't degrade over time? Right, and from a more practical standpoint, how can we deploy these models more efficiently in the real world?
Meaning, how can we make them faster, cheaper, and more accessible to a wider range of users?
Exactly, and how do we ensure that the data we're using to train these models is actually representative?
Because bias in the training data can lead to biased models.
And that would be very bad, especially when these models are used in high-stakes situations.
Indeed. And how can we better understand what's going on inside these models? And what are the limitations and biases of these models?
Right, and how can we address them?
We can also think about how we can improve these models using optimization algorithms.
And how can we use them to automate complex machine learning tasks?
These are great questions, so let's frame this conversation with those kinds of questions in mind.
Okay, so instead of just thinking about how pre-training works, because right now they're often seen as black boxes,
Yes, and how can we make them more transparent and explainable?
because understanding their reasoning is crucial for building trust.
And how can we make these models more adaptable to new tasks and domains without requiring a lot of fine-tuning?
Meaning, can we make them more generally intelligent?
Yes, and a very important question. How do we align them with human values?
How do we ensure they're beneficial and ethical?
And how do we keep these models aligned as their capabilities advance?
And what are some potential risks and unintended consequences that we should be anticipating now?
We need to be proactive about safety.
Okay, so I think that gives us some great questions.
Yeah, and it's not just us. These are questions that machine learning experts are wrestling with. Uh-huh.
Let's ask how we can make it more efficient.
Exactly. Like, how do we use limited computational resources to do pre-training?
Or maybe, What are the best strategies for choosing the right data for pre-training?
Right, and how do we scale up pre-training to even larger data sets without it becoming too costly?
Then when we talk about fine-tuning, we can ask, how do we avoid overfitting to the fine-tuning dataset? These questions guide them in the research directions they take.
So with that in mind, let's get back to our discussion about data and how it is curated.
And see what we can discover.
So, as you were saying earlier, we need to be mindful of the data that goes into training these models. Definitely not. Researchers carefully curate and select the data used to train these models. Precisely. And how do we make fine tuning more robust so it transfers well to different tasks and data sets?
And what about those different prompting techniques?
We can investigate how these techniques affect the performance of the model.
Are they all effective in the same ways, or do they have different strengths and weaknesses?
Exactly. And how do you adapt these techniques to different task types?
We also need to think about the evaluation metrics we use.
They prioritize high quality, diverse sources of information that are representative of the real world.
So it's about ensuring that the data is rich, varied,
Yes,
and reflects the complexities of language and human thought.
exactly. And they use books, articles, websites, even code repositories and social media conversations. Yeah, because how do we measure the true performance of these models, and can we make that process more robust?
These are great ways to keep digging deeper.
Yes, and with that shift, let's also talk about the data used to train these models.
Because that is a huge factor. So how can we ensure fairness and avoid biases?
Right, where is this data coming from?
And who gets to decide what goes into these data sets?
Hmm.
The goal is to expose the model to as wide a range of language styles, topics, and perspectives as possible. That makes sense. The more diverse the training data, the more versatile and adaptable the resulting LLM will be.
Precisely. And as these models become more sophisticated,
Yeah.
there's an increasing focus on ethically sourcing this data and ensuring that it represents diverse cultures and languages. And finally, we should talk about the ethical implications of these models.
Because we still need to ensure that they are used responsibly and for the benefit of all.
Okay, so we've adjusted our course a bit.
Yeah.
We're thinking more like machine learning experts now.
And we have some great questions to explore.
We'll keep that in mind as we continue, so let's dig in.
Okay, so let's go back to the point about masked language modeling, where we're hiding words in a sentence.
Yeah,
How does this method compare to other pre-training methods?
that's a great question to ask from a machine learning perspective.
We've talked about the type and quality of data, but I'm curious about the sheer scale. How much? Oh, go for it.
Can we explain the positional encoding and the rope?
It's a great question, and it's right in line with the research perspective we're taking.
Yeah, thanks for bringing that up. It's a really interesting area to explore more deeply.
So when we talk about position or encoding, we're really getting at how these models understand the order of words in a sentence.
Right, because language isn't just a bag of words.
Exactly. The position of words matters a lot, and the model needs a way to understand that.
So how does the book explain this, and what are the different ways these models encode position?
Yes, you're bringing up an important point about positional encoding, and it's a great question that a machine learning expert would ask, so let's explore it.
Absolutely. It's a crucial part of how these models understand the order of words. And what's this rope you're talking about?
So positional encodings, you see, are how these models actually know that words like cat and sat come before the the sentence, the cat sat on the mat.
Right.
Unlike some older models that process text sequentially, transformers process everything in parallel, which is why it needs this extra info.
Yeah, it's not enough for it to just know the words, but to know their positions in a sentence.
Well, a really common approach is to use positional embeddings.
Okay, so what's a positional embedding?
Think of it like adding a special code to each word, telling the model where it appears in the sequence.
So it's not just about the word itself, but also its location.
Exactly, and these embeddings are usually added to the word embeddings before they go into the transformer layers.
Okay, that makes sense. But are there different... Oh, yeah. Uh-huh.
So the rotary positional embedding.
Okay, that's a great way to put it, the road rotary.
Yes, I see what you mean. It's like how a roundabout controls the flow of traffic.
So instead of just thinking of positions as linear, like in a line.
Exactly. It's a way to think about the relationship of each token to others using rotations.
Yeah, like each token has its own angle or direction relative to the others.
That's it. And that's how we get to rotary positional embeddings, or rope.
Okay, so let's get back to it.
Yes, the book discusses a couple of different methods.
Okay, let's unpack this.
One is to use learned positional embeddings, where the model learns a unique representation for each position in a sequence.
So it's like memorizing a position for every number, is that right?
Right, and these can work well, but there's a drawback.
Uh-huh.
They can struggle with sequences that are longer than what the model saw during training.
So if the model only saw sentences with a max of 10 words,
Then it might have trouble with a sentence that has 20 words.
okay.
That's why there's another approach, positional embeddings, that can generalize. Okay, so you're asking for an example of another method of positional encoding, specifically talking about rotary positional embeddings.
Yeah, you're jumping right into the really interesting details of this, and it's great.
Right, this is where it gets really fascinating because there's more than one way to do positional encoding, like we just touched on.
And this rotary approach, or rope as it's called, is a really cool alternative to those regular positional embeddings.
Exactly. You see, instead of adding a static code to each word, rope uses rotation matrices to encode position.
So it's like each word is rotated by a certain degree depending on its position.
Precisely. And the amount of rotation is determined by a mathematical function, kind of like a sine or cosine wave, but in multiple dimensions.
So as we go further along in the sentence, words would be rotated at different angles.
Exactly. And this allows the model to capture relative positions, not just absolute positions.
Okay, what does it mean to capture relative positions?
It means that the model can understand that the word at position 5 is, say, 2 steps away from the word at position 3, rather than just knowing they're at specific positions.
So it understands the relationship between words. What are those?
Exactly. So we use positional encodings to inject information about where each token is within the input sequence.
The most common way is to use sine and cosine functions.
Right. And the math for that is in the book, and in more detail than I want to go into here. But the key idea is that every word gets a unique position value.
Okay, so this positional encoding is like adding a unique fingerprint to each word based on where it is in the text.
Precisely. And when you ask to expand upon this, we could think about what is called rotary positional embeddings.
Okay, what's that?
The book talks about extrapolation and interpolation.
Extrapolation and interpolation.
Exactly. Extrapolation is about extending what the model already learned to new positions.
Can you give me an example?
Sure, imagine you have numbers 1 to 10, and you need to understand 15. Yeah, think of it like a clock, and the hands move differently at each position, encoding different relative positions.
That's a good analogy. So what's the benefit of using rope over those standard positional embeddings?
Well, rope, for example, allows the model to extrapolate to longer sequence length better, which is something we'll talk about later.
So if it has a sequence of 10 words, it can apply that to a sequence of 20 words. That makes sense.
Exactly, and it also helps the model in tasks like language translation, where the word order may shift across languages.
Okay, so rope can keep that relationship between the words intact, even as the order changes. Okay.
Well, the book touches on this. Basically, instead of using those sines and cosines, it uses rotational matrices.
How does that help?
It allows the model to explicitly reason about relative positions of words and how far apart they are from each other.
That makes sense. So instead of just knowing the absolute position of a word, it also understands its position relative to the other words.
Yes, it's like having a dynamic changing coordinate system for each word that is then captured in the key and value. Yep, that's one way to think about it, and that's a key part of what makes the transformer architecture so powerful.
Right. It's all about understanding the subtleties of language. And these techniques are how the models do that.
So, with that in mind, let's continue our discussion of different positional encoding methods, and we can compare some of the.
Oh, back to our listener. What's up?
Can we continue to discussing the linear transformer? Does the linear transformer?
Oh, absolutely. That's a great question. And it's right in line with what we were just talking about.
Yeah, thanks for bringing that up. It's a very important concept in the field.
So you want to know more about the linear transformer specifically and how it compares to the standard transformer, right?
Right, this is another way that researchers are trying to address some limitation of the basic transformer.
And it's all about efficiency, which we've touched on quite a bit during the show.
Exactly. Let's dive in and explore some of these ideas, keeping your questions in mind.
Okay, so as we were saying before, the transformer is powerful.
But it can be computationally expensive, especially when dealing with long sequences of words.
Right, and the attention mechanism, while amazing.
It has a quadratic complexity with respect to the sequence length, which means as the sequence grows, it gets very slow.
So what's the solution? That's where these linear transformers come into the picture.
They aim to approximate the attention mechanism with a linear complexity.
So instead of the computation time growing at a rate of n squared, it grows more linearly, like the number of words.
Yes, and that's a major difference that lets them deal with much longer sequences.
And one way to do this is by using low-rank approximations.
Which essentially means representing the attention matrix using smaller matrices.
So instead of doing operations on a large matrix, it simplifies it.
Yeah, and this approximation significantly reduces computational cost.
That makes sense. And the book mentions that the full transformer has quadratic complexity due to the dot product attention.
Right, and that becomes the bottleneck when you're processing longer sequences.
So these linear transformers try to avoid those calculations.
Exactly. They do this by rewriting the attention matrix as a product of two matrices.
And this changes the computation time from quadratic to linear.
Yes, and this makes it easier to process long sequences.
Okay, so we've talked about how they improve efficiency.
And this linear approximation allows them to handle those long sequences of text that might be too slow for the original transformers.
What are some of the specific methods used in linear transformers?
One common approach is to use kernel functions to approximate attention.
Kernel functions, like in other machine learning.
Exactly, like in support vector machines where you're mapping the input to a new space. In the linear transformer, the kernel computes the similarities between words more efficiently.
Okay, so instead of computing all the dot products directly,
You're using a kernel to calculate similarity, and it's much faster.
and this allows the model to focus on the most important relationships.
Yep. And another approach is to use a low-rank matrix decomposition,
And what does that do?
which basically means representing the attention matrix as a product of two smaller matrices.
So that the operations can be done on a much smaller scale.
Right, and this reduces the complexity of the computations significantly.
There's a trade-off, right?
There's always a trade-off. It's not magic.
I imagine that by using linear approximations,
You lose some of that expressive power of a full transformer.
okay, so it can't understand everything perfectly.
Exactly, because you are approximating a matrix, which means you are losing some information.
Right, and that means these linear transformers may not be suitable for every task.
Exactly, you have to choose the right architecture for your job.
So for tasks where it's important to understand really complex and nuanced interactions,
A standard transformer might be necessary, despite the computational costs.
and for those tasks where efficiency and speed are more important than a perfect result.
Then a linear transformer might be the right choice.
Okay, so it's like, how much efficiency do you need versus how much accuracy can you sacrifice?
Right, you have to balance what you need and what you can get.
So they're not better or worse, but good at different things.
Exactly, and this book, which we have been using,
Yeah,
it also touches upon different ideas for long sequence modeling.
which we have been building up to through our discussion of positional encodings.
Yes, because these models need to somehow handle more than a few sentences of text.
So these methods can be applied to these linear transformers as well.
Absolutely. Techniques like the rotating positional encoding we were just talking about.
And also relative positional encoding.
And also they can also be used with those methods to improve performance.
Okay, that makes sense. So linear transformers are not just for efficiency.
They are, but it's also about how these models can better handle long sequences, which is really important.
And so these linear transformers don't use the full attention mechanism, as we said.
Right. They use an approximation method, and it's to make it more efficient and better for longer text.
And when we were discussing the various positional encodings,
Yeah.
we talked about how transformers are able to process all the words in parallel, which means they need the extra position info.
And those techniques are usually also used in a linear transformer model.
Because they also need to understand the order of words.
Exactly. They also need that context, even when the model is linear.
Right. So from a machine learning expert's perspective.
Yeah, we can ask some questions, such as, how well does a linear transformer approximate the full attention mechanism?
Or how do the different approximation techniques compare in terms of speed and accuracy?
And are there ways to further improve the efficiency of linear transformers?
Or how do we choose the right linear transformer for a given task?
These are excellent questions, and there are more open questions for machine learning experts to investigate.
So we've talked about these linear transformers and their computational advantages.
And, those are crucial for scaling up LLMs, especially as people work with longer and longer text sequences.
So while those dot product attention models are accurate, they're also inefficient.
Right, and those are not suitable for long sequences because they're too slow.
Oh yeah, go on.
Can we summarize the prompt technique and then jump to the alignment?
Okay, that's a great request.
Yeah, absolutely. Let's do a quick recap of prompting.
So we've discussed how prompting is the way that we communicate with LLMs.
It's about carefully designing the input to get the desired result.
And it's a lot more than just typing in a question.
We saw that you can provide examples or chain of thought reasoning.
as well as soft prompts that interact with the model's internal state.
And we've talked about different types of prompts and how important it is
And all of these methods require thinking like a researcher.
to investigate how effective they are for any given task.
So let's summarize those now before we move on.
Yeah, that's a great idea. Thanks for keeping us on track.
Okay, so as we were saying, prompt engineering is very important.
And it's all about how you craft your input.
It's how we get a model to do what we want,
So it's about strategically constructing the prompts.
to align with the model's capabilities and biases,
It's about speaking the model's language.
to guide its output and get better results.
And a well-crafted prompt can make a big difference.
In getting a relevant, accurate, and insightful response.
Okay, so there are some ways that we do this
One way is to provide context in the prompt.
to help the model understand the task at hand,
It also helps to specify the format of the output.
such as if you want the model to output a list of bullet points
And finally, we can use specific keywords or phrases.
to trigger certain responses in the model.
Okay, so with that summary of prompt techniques,
And thinking about how to choose the correct one.
let's talk more about how different models handle those prompts.
And that is where these linear transformers come into play, making it easier to process those long text sequences.
Yes, and from a research perspective, that's how we improve these models.
So with this linear approximation of transformers, we can handle those longer sequences of text without sacrificing too much performance.
Yeah, and there's a lot of ongoing research to further improve these models and make them more efficient.
That makes sense, and it's a really important step in making AI more accessible.
Precisely. And that wraps up our look at the linear transformer.
Okay, so we've touched on positional encodings,
Right.
and now we've looked at these linear transformers, but we also mentioned relative positional encodings.
Yeah, and we should talk about those next because they're an important concept that are also very relevant.
So let's get into it. What are those?
Well, instead of encode, yep, go on.
Can we just go to the alignment part and do the write-up of the whole book?
Okay, sure, that's a great idea.
Yeah, thanks for letting us know what you're most interested in,
It sounds like you're eager to get to the heart of the alignment challenge.
which is about ensuring these models act ethically.
And in line with human values, it's definitely a crucial area.
So let's skip ahead to that section of the book.
We can always circle back to some of those other topics if you'd like,
Absolutely. So we've talked about pre-training and prompting.
which, sets the stage for this next important part.
Okay, so alignment.
Right, and that's about how we guide LLMs to behave as we want.
And the book emphasizes that alignment is key to responsible AI development. Okay, I hear you. You're really eager to get to the alignment part.
Yeah, and it sounds like you're ready to move on from these technical details.
So we've talked about pre-training, generative models, and prompting.
Right, we've covered a lot of ground.
And I understand the interest in talking about how these models behave ethically.
That's the crucial part, and it's also one of the last topics in the book. Yes, the goal is not just to make LLMs accurate, but also safe.
So we want them to be unbiased, truthful, and harmless.
Exactly, and this is much more complex than it sounds.
Because human values are diverse and sometimes hard to define.
Right, so how do we teach a machine to understand ethics?
Well, one approach is called instruction alignment. So let's jump right into it and talk about alignment and why it's so important.
Okay, so as we've mentioned before, alignment is all about ensuring that LLMs are aligned with human values.
It's about making sure they're helpful and harmless.
It's also about making sure that they don't cause unintended consequences.
Exactly. And this is a really complex issue.
Because how do you even begin to define human values?
Right. And how do you teach those values to a machine?
There's a lot of active research in this area.
But one of the most common methods is called reinforcement learning from human feedback.
We briefly touched on that earlier, and we can go into that now.
Yes. And how does that work exactly?
Well, in RLHF, humans provide feedback on the model's outputs. And that involves fine-tuning the model on data that has instructions.
So we basically show the model what the expected behavior is,
And there are several different ways to do this.
such as supervised fine-tuning, which we have mentioned before,
Yes, and that's where we train the model on labeled data.
that has instructions and corresponding outputs. They rate the responses that the model gives.
And this feedback guides the model to produce more desirable behavior.
So it's like giving the model a reward for acting ethically.
Exactly, and this process involves creating a reward model.
And that reward model is trained on human preferences.
And it also captures the subtleties of human value judgments. It's basically training data that has examples of what we want.
So you give it a task, like translate this into Frenches, and then show the correct result.
Exactly, and this helps the model to understand our intentions.
And adapt to the tasks that we give it.
Right, and the book talks about acquiring the data used for this.
Because it's not as simple as just grabbing text from anywhere. So the model isn't just learning to be accurate.
It's learning to act in a way that's safe, beneficial, and ethical.
And this also brings up a great point about biases.
Yes, bias is a big concern.
If the training data used to train the model is biased, then the model will be too.
And that's why it's so important to ensure data diversity. And then there's the whole issue of fine-tuning with less data.
Because labeled data can be expensive and time-consuming.
And then there are other methods to improve the models.
Such as instruction generalization and even using weaker models.
To improve those bigger, stronger models, which is a very cool idea.
So it's about making this fine-tuning process more efficient.
Because ideally, we don't want to use massive data sets.
Okay, so what else does this alignment part of the book cover?
Well, there's also human preference alignment, and that's a huge area.
This is where the model learns from human feedback, right?
Exactly. And one method for this is RLHF, or reinforcement learning from human feedback.
RLHF, that's what we talked about a little bit earlier. And it's also why it's important to have diverse teams of people working on this.
To ensure that the models reflect different values and perspectives.
So these models aren't just learning to be accurate, they're learning to be fair.
Yeah, and there's also this idea of transparency.
Yes, because how do we know if the models are acting ethically?
Well, we need to be able to understand how they're making decisions. Yes, it involves training a reward model to predict human preferences.
So that the model will start to understand what humans like and dislike.
And then we use that model to fine-tune the LLM.
And push it in the direction of more desirable behaviors.
And as you can imagine, this involved a lot of careful thinking.
Because it's not always straightforward to define human preferences.
So this part of the book goes deep into that.
Now, we've also talked about these step-by-step approaches.
Right, like chain of thought, it also plays a role here.
Because we don't just want the model to provide the answers.
We also need to know that the model is reasoning correctly.
So step-by-step approaches also have an alignment.
Oh yeah, let's hear it.
So the process to press the alignment is the step-step alignment. Is that right?
Okay, that's a really interesting way to put it.
Yeah, you're highlighting how alignment isn't just one big thing.
It's actually a series of steps, and it sounds like you're really honing in on that aspect.
And it's interesting that you call step-by-step alignment a red.
Like a crucial area of focus that we really need to pay attention to.
That's a great point. It's like saying that if we don't get the steps right, we won't get the final alignment right.
And this ties back to the chain of thought prompting we discussed.
Because it's all about understanding the reasoning process.
And when we're talking about alignment, it's about the why behind the output, not just what.
So we need to be able to interpret their thought processes.
And we can do that by using the chain of thought prompting we talked about earlier.
That's right. So it's not just about what it does, but why.
And this is how we build trust and ensure that the models are acting in accordance with our values.
Now, we've already talked about how these models are trained.
Right, we touched on pre-training and fine-tuning.
And now we can see how that is all related to alignment.
Because the data you use and the way you train the model affects everything.
So we need to be mindful of that throughout the entire life cycle.
And also, it's important to make sure that they align with human values in the long term.
What do you mean by that?
Well, these models are constantly being improved and updated.
Right, and we need to make sure that they remain aligned even as they evolve.
Exactly. And finally, there is also inference time alignment.
Which means we can align the models even without more training.
And the book explores these various approaches in detail.
It's like they're trying to make these models not just smart.
But also, good citizens in the AI world.
Right, they're trying to make sure they act responsibly.
So we need to keep evaluating them and make sure that they continue to act responsibly.
Right, it's an ongoing process.
Exactly. So it's a continuous process of learning and adapting.
And we also need to be proactive.
We need to anticipate potential risks and try to address them before they become a problem.
This includes being mindful of unintended consequences.
Yep, we don't want any surprises from the models.
Okay, so we talked about the data that is used for these models.
Yeah.
And how they can create unintended consequences.
And this also ties back to those prop techniques.
Yeah, it's all connected.
And this whole area of alignment is all about mitigating those risks.
Okay, so now we're really getting to the ethical heart of this topic.
We are, and it brings us to the core of what makes LLMs useful.
Because we want these models to be both accurate and beneficial.
And this alignment is a very complex problem.
And it requires a multifaceted approach with these different methods.
Exactly. There's no single solution that fits all situations.
Okay, so this section of the book really digs deep into the practical methods.
Right. It's not just theory, it's how we actually get this done.
And how do these ideas connect to those ideas we were discussing earlier?
Well, things like positional embeddings and linear transformers.
Yeah.
They become even more important when we are trying to train with less data.
Yes, and we can use those to guide these models to act ethically.
By carefully designing our instructions, we can steer models toward more desirable behavior.
Okay, so the data, the model, and our prompts need to be in agreement.
Yes, they need to work together to achieve alignment.
Now, from a machine learning expert's perspective,
What are some questions we could ask about alignment?
yeah, how do we measure alignment and how do we know that our models are safe?
Or are our current techniques sufficient, or do we need to develop new methods?
What are the limits of current alignment techniques?
And how do we ensure that alignment holds in the long term?
Or how can we automate this alignment process?
And that's a really important question because it can't be just a manual process.
And you'll see in the book there is a connection between all of these concepts.
Okay, so even though we are skipping ahead,
Yeah,
we can still relate it back to what we've already talked about.
absolutely. And it all ties together in the goal of creating useful LLMs.
So, with that in mind, let's dig into this alignment section.
Right. So how do we scale up the alignment?
And what are the potential risks that we need to anticipate?
And also, how can we balance innovation with safety?
All excellent questions, and they really get to the heart of the matter.
So alignment, that's not just something you can do once.
It's a continuous process of monitoring, evaluation, and adaptation.
Okay, let's start by talking about supervised fine-tuning, or